So I think we are live now, right?
Yep, go ahead.
All right, so peer-to-peer networking strategies in multiplayer games, hosted by myself. Who am I? My name is Brandon, for those who don't know me. I'm the second year computer science course rep, and I'm normally interested in tools behind video game development, so your engines, your libraries, debuggers, IDEs, dev kits, all the shebang used to create video games. And the talk today I'm going to be doing is on the networking side of things. So the first question we need to tackle is, what is networking? Networking, as you probably know if you've done the second year networks fundamental module, is in a word, it's pain, but in a few more words, it's a good way to actually get computers connected to each other and the ability to interact. So computer A can send stuff to computer B, and computer B can send stuff to computer C and whatnot. This makes video games quite interesting because then we have the advent of multiplayer games. And multiplayer games use usually one of two networking paradigms. So you have the client server and the client-to-client method. Client server is everything, each of these PCs connect to one box, and that box normally holds the game state. So if any of you have played Minecraft before, then you'd host a Minecraft server on a PC or a server, and each player connects to it, and the server uses a thing known as ticks. So a player will do an action, and the server will tick over and take that action and produce a result on your screen from their updated game state. So I don't know if you've ever had lag in a Minecraft server before. I know I have multiple times, where I've broke a block, like a wooden tree, and it'll just spawn back on the screen. The block will disappear on my screen, but show back on the screen like a second later, and I'll be like, what the hell? I just broke the block. Why is it not giving me the item? And that's because of server ticks. So there is also the client-to-client method. So every PC holds their own version of the game state, and when one of these PCs updates, it sends out essentially a notification to all the other PCs on the network that the game state has been changed. So, like, if I broke a block on my screen, then the game's like, okay, we've broke it on my screen, now we need to update everyone's game to match what's shown on my screen. And there are multiple different ways of keeping these versions of the game in sync. Most client-to-client games usually follow the client-server model, but hosted on one of the player's PCs. I don't know if you guys have played one of the older Call of Duty games, but this used to cause a phenomenon called host buffs, or like host priority, where the person hosting the game would have basically zero lag to the server, and normally cause them to have quite a large advantage over the other player. So why would we ever use a peer-to-peer server connection, if a client server can handle things a lot better? Well, the main advantage to having a client-to-client connection is there is no middleman. So each of these has to upload. Like, let's say this PC wanted to upload. It's reliant on the upload speed of this connection to here, and then this PC is reliant to the download the upload connection of this server and the download connection of itself. If we just eliminated that, then this PC could connect to this PC directly, and the speed is only dependent to the raw combined connection of the two clients. It's very inexpensive then. You only really need to run a server if you're doing extra stuff on the side, like matchmaking and keeping player stats in check. But other than that, the game state can be hosted on each PC, so each PC can run the calculations necessary to actually play the game. And therefore, there is no central point of failure. If this server goes down, each of these PCs will no longer be able to play the game. One of my favorite games at the moment, Final Fantasy XIV, goes down for maintenance, and when it does, it takes an entire day to update, and it's a pain because then I can't play one of my favorite games. But that's just how it goes by having a client-server relationship. The issue with peer-to-peer is that it's harder to implement because each of these PCs has their own version of the game state. It's hard to keep every PC updated with a valid updated version of the game state so that the PCs don't desync and cause issues. It's also harder to detect cheating because each of these PCs, if one of them cheats, the server can handle the cheat detection and essentially boot this person off the network. But on a client-to-client relationship, you need to have very strong client-based anti-cheat, like easy anti-cheat or something like that, so that if someone does cheat or attaches a debugger to the process, the client will detect it and essentially stop itself from sending any data to these, so that a botched up version of the game state doesn't get created. And it's also hard to push updates. Since all of these are running their own version of the game, they need to be able to run the same version, otherwise they may desync and not even be able to matchmake properly without any sort of issue. So normally there is actually a server. I know we want to eliminate servers, but sometimes you have to run one just to send updates to each person on the network so that they can actually get a version of the game that can connect to everyone else. So if we want to connect, let's say in a simplified case, we want to connect PC A to PC B and have a simple 2-player video game that we want to have send the game state between each other and have a very low latency experience. How do we do that effectively? So there are mainly two ways of handling this issue, and that's delay-based netcode and rollback netcode. I will start by going through delay-based netcode and then move on to rollback netcode shortly afterwards. So how delay-based netcode works is it adjusts the inputs for the latency of the connection. So before I show this video, I'm going to have to give an explanation on how these video games work and how the system works. So most video games handle stuff in frames. So the modern video game normally runs at around about 60 frames per second. And how ping works is once you ping someone and you get it back, you'll have a time which it takes to be sent from your PC to the other person's PC and back again. So let's say I send a ping. Let's say player 1 sends a ping to player 2 here. And the ping results in 90 milliseconds of delay. So it takes 90 milliseconds to do a complete round trip from player 1 to player 2. This means that it takes 45 milliseconds, so half that, to send player 1's inputs to player 2. And 60 frames per second means that each frame is around 16.6 milliseconds. Let me just take a drink right quick. So if player 1 takes around 16.6 milliseconds for a frame and 45 milliseconds to send from this person to this person, that's around 3 frames of latency between each player. And the way delay-based netcode handles this is it delays the inputs by those 3 frames and then has an updated version of the game that should sync on both players' screens in order to produce the actual game state. So if I play this video right here, each player presses a button on the 3rd frame and it comes over on the 6th frame because they handle the delay with 3 frames of latency between each player. So this works. It definitely does keep the games in sync, but there are issues mainly to do with the fact that you have to delay your inputs on your side to the opponent in order to have a synced game state. And since networks are not the most stable thing in the world, you can have packet loss and unstable connections. So when your connection spikes, you may suffer what's known as a stutter or a lag spike. So as you see here, the connection drops. And that wasn't a pause for effect, by the way. That actually happens in the game. It stutters, and you may think, oh god, why does that happen? And the reason why that happens is because player 2 is sending data, and the connection cuts out. And the game has to wait what would normally be the amount of time to actually gain the frame on the other screen in order to keep the game rolling. So as you see, let me show that again just to make things a bit clear. That's when the connection drops. And since the second frame here is not actually sent, what would be the fifth frame, it needs to sync. So it waits and then sends. This is quite bad. This is very bad. You can imagine if you're playing a game and you can't receive the opponent's inputs, your inputs might actually be taken away into what's like known as the void. And this can be a problem, especially in games where input accuracy is very important. So how do delay-based games deal with this? Well, they would have a change in their delay. They would keep changing their delay to handle the packet loss or unstable like change in ping from player 1 to player 2. And this does stop stutters in a way. That's just the video stuttering, by the way. It's not actually the game. But it also creates a very unstable environment where gameplay online feels completely different to gameplay offline. It's, in my opinion, this isn't enough. The detrimental effect of input delay is the inherent input delay, where offline and online can feel completely different and be completely different experiences to each other. Habits such as multi-shining, you see a little fox over here, and Kazuya over here. As you can see, the shine is on the right side, and it does a little bit more damage to the one on the left side. These are both what's known as frame perfect, so you actually have to hit the button on that frame, otherwise the move will not have the intended outcome that you want it to do. And you can imagine in a delay-based solution that this is very hard to do because you may be trying to do the move and your input's delayed, or you get a stutter and it just feels off. You feel the stutter and you just don't get the move that you want, and it's very frustrating. It's very annoying. Imagine doing this. This is Evo moment 37. So each of these parries that Ken does is very tight. If any of these stutters, he would die and Chun-Li would win the round. But in an amazing turn of events, he actually managed to win this. This was in 2003, by the way. A very long time ago when we could actually have offline tournaments without fearing of infecting someone with a deadly virus. So the more effective way of handling the syncing of two machines is using what's known as rollback netcode, where the entire purpose is to rewind and re-simulate the game. So this is where stuff gets complicated. So let's say that these two players here, sorry, I forgot to add the game. This is Killer Instinct 2013 for the Xbox One, and it came over to PC and PS4. It's an amazing game. I recommend you all check it out. It's got the soundtrack by the composer who did Doom and Doom Eternal, so you know it's top quality. So let's say that the connection here is, again, 3 frames, 45 milliseconds of ping between two players. What actually happens is, I'm just going to pause it here. Player 1 doesn't have a remote or a delay. Once you do the move on the player 1 side, it happens. It happens on your screen. It'll happen on his screen as well. What actually would happen is, let's say I use a move and the opponent does the same move on the first frame. We actually get it on the 5th frame, but the game in the background between these sequence of events, it actually re-simulates the game behind the scenes. It does 4 frames worth of calculation behind the screen, and then on the 5th frame, the move carries on like nothing happened. Does that look like lag? Let me show you again. So player 1 does his move on the 1st frame, comes out, and player 2 sends theirs over on the 5th frame, but it actually technically comes out on the 1st frame. It just carries on from the 5th frame as our game state is updated. This is known as a rollback. Let me just... So how do we handle packet loss in an environment like this? So the way we handle packet loss is we can use a very accurate way of predicting what the opponent's going to do. And how we handle this is we can predict the last thing that the person, the remote player, inputted is going to be the exact same thing that they do on the next frame. And remember, frames are 16.6 milliseconds. Think about how many times you actually change your inputs in a video game. Unless you are pressing buttons like a madman, you are not actually changing your inputs that often. So let's say that the person on the right's inputs conk out on the 3rd frame. So the game just keeps going, keeps moving forward, and then once we get the updated inputs that the opponent has, we resimulate and keep going. If there is no change in the game state, the game acts as if nothing happened at all. Magic, right? It's quite an interesting way of doing things. So let's say that person here does more buttons. So he doesn't do the exact same thing on every single frame, and instead varies up a bit. So player 2, let me just pause that, starts off with this button. So since we get his button on the exact same frame that he activates it, he starts doing the thing, and then we start getting more inputs that he does. And we actually then resimulate the game from that frame to see if anything changed. If nothing changed, like if there is no change in the game state, we carry on like nothing happened. We resimulate, and if the simulation is the same, there is no reason to change what player 1 sees. This makes the game run a lot better, as you can imagine, because you're not stopping and starting and stopping and starting. Instead, you carry on, and if there is a change, you resimulate and give the updated version of that game state to both players. So you may think, is predicting the game actually good? And the answer is, yeah, you'd be surprised. So if we predict what the opponent is going to do is the same thing as the last frame, that prediction is correct around 95% of the time. And if that prediction fails, a teleport may occur. This may be 1 to 2 frames. And this is better than a delay-based option, because there are many times in a game where your inputs will never actually affect the game state, like being mid-combo, for instance. So if I can just move back real quick. What you see here is Lynn is being comboed, but you can imagine her inputs aren't really going to do anything to the game. So why is there a stutter where there shouldn't be a stutter? Like, her inputs aren't going to do anything. What's the point of pausing the game? Well, in a rollback solution, that will never happen. Your combo just keeps on going unless there is a reason to like change the game state. And this is really important for this game, because this game has stuff that you can do mid-combo, such as combo breakers or shadow counters and stuff like that. So prediction seems quite good, right? But there are ways that we can improve the way that we can minimize these teleports. So we can split the difference. Inputs will always take time to travel across a network. So what we can do in a rollback solution is we can actually have around maybe 1 or 2 frames of input delay, which we have on our machines, so that the inputs have a higher chance to sync when they want to sync, and that means that we don't need to teleport as often. And if anything gets out of that range, instead of stuttering or having any sort of packet loss issue, it just teleports back and everything seems relatively stable. You may have to adjust your own muscle memory, but the gameplay remains in a stable state of not stuttering or not having any syncing issues, and everything seems to be quite good for both players, each player having a more fun experience. You can imagine that a delay-based solution would actually be worse for connections that go far. So let's say I wanted to play my friend in the West Coast. Normally, those connections will be unplayable. They would have around 10 to 11 frames of delay. Everything would feel bad. The connection will be fluctuating. There may be insane packet loss. But by using rollback and a few frames of input delay, those connections become way, way smoother. So how do we actually build a rollback solution? You may think, Brandon, this sounds amazing. This sounds super, super good for my game. How do I actually make it? So you need to separate your gameplay from the presentation. What that means is you essentially need to play the game with the monitor turned off, which may sound really weird, but you need it to resimulate the entire game. You need a serializable game state, and what that means is each frame, you need to essentially store it in a gallery and be able to take that frame and put it back where it was before so you can resimulate the game. A poor example of when rollback is implemented is in Street Fighter V, and this was a real big issue on the PS4 because frames would drop like crazy, especially if one person's PS4 would overheat. It would cause, doesn't this just look terrible? This looks so bad. As you can see, Ryu's just playing the game like he normally would, but Akuma over here is teleporting like a madman because he's dropping frames. And there are ways to deal with this, which I'll talk about in a second. There are libraries that we can use. So yeah, making a rollback-based solution isn't going to be easy. And lots of studios have actually tried to make rollback solutions in the past. Many have failed, many have succeeded, and the ones who have succeeded really do reap the rewards of having good online play. So there's this library called GGPO, and it's great. It's programmed in C, which may mean that it's hard to actually port it to the engine of choice that you're using, but there are many bindings created for certain engines like Unity. You just have to make sure you build your game with rollback netcode in mind. What this does is it actually tells you when your games are out of sync and how much, and it also keeps a buffer of the inputs that are sent from each party. So you can basically do the exact same thing as in this example, where if there's packet loss, you can queue up the inputs and resimulate the game based on new information. The actual rollback itself is dependent on you because it's your game, and the way that different games handle the rollbacks are completely different to each other. Essentially, if you wanted to make a bog standard rollback, you could just rewind, resimulate, and update the game state, but this can cause issues as shown in this example. So you have to really tune it to your own video game, which means that it is hard to implement. Even with specific software libraries that we have, creating these rollbacks is very hard to do, especially in games that aren't deterministic. And what I mean by that is if your game inputs on both sides, let's say you're running a game with the exact same inputs, these simulations need to be the exact same. And what I mean by that is like, if you have a replay system in your game, you can essentially feed the inputs into it and have it a complete reenactment of the game, which means stuff like random number generation. So stuff such as random items, random anything in a game can make it really hard to resimulate, especially if the way that you're doing it isn't dependent on what's known as a RNG seed, because normally you could just save that seed and resimulate the game with the RNG from that seed. The technical cost of resimulation also may push you over your performance budget. You may need to simulate onwards of like 10 frames in one frame, which is extremely hard to do, especially if you're trying to like optimize the game as much as possible. You may need to turn down your physics engine and that. But Mortal Kombat 11, surprisingly, has made rollback work on the Nintendo Switch, which is, it's not the most powerful console in the world, but it's powerful enough that it can actually handle a huge game such as Mortal Kombat's rollbacks on a very small scale. Speaking of Mortal Kombat, the engine, Unreal Engine 3, that was used to make Mortal Kombat 10 and Injustice. I'm pretty sure it was Injustice 1. Took over 10 years to redesign the entire engine with rollback in mind. So you may think, Brandon, please, it's so hard. Why would I have to do this? Like, what's the point? And the point is, it's worth it. It's incredibly worth it in the long run. These very old games, such as King of Fighters 2002 Unlimited Match and Guilty Gear XX Accent Core Plus R, had a huge resurgence. Look at those player numbers. They were averaging around about like 200 players and shot up to 2,000. So that like games increased tenfold in player numbers. Sure, they like stabilized a bit higher than they did, but for some games, this is enough to breathe new air into it. I don't have the numbers for it right now, but Super Smash Bros. Melee, a like version of the game, was created for like emulation purposes, which has a rollback netcode solution, and that game has been blowing up recently. It's quite nice to see, and having good online play is more feasible. Like, it's extremely important in a world where offline play isn't feasible. Like, of course, right now I can't go see my friends. I can't have a zero frame delay perfect like connection game with someone offline, because I can't go offline without risking my family and my life and their own lives. So it's very important to have good netcode solutions. So thanks for listening. That's pretty much it. I can answer any questions that you may have. The videos were credited to Infilament of ki.infil.net. I recommend going to that website because there is more information on rollback and more like a deep dive into some very technical language of how the solution actually works. And Code Mystics and Keats, who designed the rollback for Killer Instinct, also did a very, very large GDC talk about how NetherRealm actually made the rollback solution for the Mortal Kombat game simulate essentially 10 frames in like a fraction of a second. That's all. I can take questions if anyone has any, but I believe that's everything. Let me just check the troop real quick. Other than that, I hope my talk went well, and I really hope you guys enjoyed it. Can you use AI to correct for the packet loss? Yes, actually. There's been talks about incorporating a like a version of the prediction using a neural network. But what many people have found is that like using a neural net is good, but it also doesn't really have the trade-off of running like a huge neural net to maybe increase 1 or 2% of the like of the prediction. So like maybe you'll go from a 95 to a 97 or a 98% prediction, but that's normally not worth the overhead of having such a large system playing whilst you're also trying to run a fully fledged game. But yeah, it's very interesting. Maybe in the future when AI becomes maybe a bit more lightweight to run, or technology surpasses that front of like not being able to run AI very well, as some solutions may require like proprietary hardware, such as NVIDIA's CUDA solution. It might be quite an interesting thing to look into. Other than that, I do not see any more questions. Thanks, Chris, for the question on the stream. And I think that's it. thanks everyone, and goodbye. Also tune into the other Enhancement Week events. We've got quite a lot of good stuff going on. Thanks.